So welcome back, guys. Now we'll resume our lectures with Thomas Britton, who's a staff scientist here at JLab. And he will be starting the series of data quality monitoring with AI, like quantum computing. Okay.
Yeah, so I'm Thomas Britton. Before being a staff scientist here, I was a postdoc in Hall D. So a lot of the early parts of the Hydra work came because I was a postdoc and didn't want to do certain parts of my job anymore. And that's the prime motivation for me as a human being. So before we get into Hydra and the exact application, I was asked to do a little bit on machine learning, intro to machine learning, which is a very daunting thing to do. You can take any one of these little tiny nodes at the end of this tree of machine learning and spend a decade truly understanding it. I don't think I have that much time. So instead, what I thought I would do is try to give kind of a cursory overview with some key ideas. What is machine learning? What are the basic tenets? And how do the underlying kind of mechanisms work at a high level? I'm going to be sparing on the math. You can either dislike me for that or thank me for that, depending on your your love of the inner workings of the mathematics of machine learning. If you download the talk, each section will have a link at the top. See, like this one. You can click on that. It will take you to a web page toward data science, which I have found to be a fantastic resource. It starts getting into the nitty-gritty math and how that stuff actually works. So I did collate those for you there. But let's start with, there are three main kind of categories that you could think of when you hear machine learning. Often people will say AI, and AI people tend to not like that because if-then statements are AI. It's an artificial way to make decisions. If a number is greater than 3, do this. If it's less than 3, do that. If it's equal to 3, do a third thing. But whenever people say in pop culture AI, what they probably refer to is ML. And most commonly, supervised learning gets applied a lot. It's kind of the best one. It usually uses subject matter experts, and you can do classification with it. So that's a dog, that's a cat, that is a truck, and regression problems. So when we get into things like track reconstruction, where you want to know the momentum of a particle, and you're trying to estimate it using maybe supervised learning techniques, that's you're getting into regression. So you get out a number here. Typically in classification, you get out a set of numbers, and the highest one represents the bucket that wins, the classification that wins in a one-hop classification. Reinforcement learning tends to be, when I started getting involved with this, my child, I had a son, he was, 1.5, 2, and I was starting to learn about machine learning and realize that it's exactly what I was doing with my son. So the child takes some action, is in some state, takes some action, and then the parent goes, no, don't do that. Or good job taking a step. And through that, learns a policy of behavior to move about the world. And then unsupervised learning is the thing that Netflix kind of built their entire business model on. It's the thing that teaches you that you are not nearly as unique as you would like to think you are. That there are, out of the billions of people on this earth, many people like you. So let's dive into reinforcement learning a little bit. So generally, this is useful to solve problems with competing objectives. So if you're going to drive a car, you have to look out, you have to see what's in the road. Do I drive left? Do I drive right? You're making these decisions based off of the state of input. This road has a green light. This one should have a red light. There should be pedestrians here to watch out for. There's a bus lane, a bike lane. These are your kind of state variables. And then you take some action. Speed up, slow down, turn right, turn left. And it tends to be state dependent. Yes, there are specific applications which kind of blur the line. Game AI is often this. So Alpha, their Google Brains played StarCraft. For those that know, it's a very complex game that you have to take in what the opponent's doing. You have to manage your resources. You've got to do that. So like one of the world's best StarCraft players is a machine. So typically what they do is they have the machine play itself a bunch of times. It learns the state. It learns what policies should be taken, what actions should be taken depending on the current state of affairs. And I like the self-driving analogy because I think it's big in pop culture. How it actually works. I typically like asking myself, can you make mistakes while learning? So self-driving cars. Usually reinforcement takes a long time to learn the right policies. You aren't going to be Tesla and just be like, go out on the road, and if it crashes, we'll learn something. NTSB probably would frown on you. People would not get in the car. It doesn't know how to drive. It doesn't know how to walk. It doesn't know what signs mean. Go forth. So usually you rely on simulations to jumpstart this process. You rig up a simulation of driving that's adequate to start learning, oh, when I press on this pedal, I go faster. And maybe that's what I want to do, maybe it's not. You can go on YouTube and do reinforcement learning, and people make game AIs to play Mario and whatnot based on that. And you're trying to learn an optimal policy or set of policies. So the general thing is, given the state of things, what action or actions can be performed to maximize my reward? So it needs to be state dependent. You got to somehow say, we're playing a game of chess. How is the board looking like in terms of a quantitative measure? Is this better for me or worse for me? What actions can I take? Car can't drive in the 8th dimension, as far as we can tell. So if you don't know what you can do, you don't know how to modify the state. And then there's this reward. If your AI starts doing crazy things, it might be that you're giving it the wrong reward. If you play Grand Theft Auto rules and you say you get points for running over pedestrians, you may learn bad policies for a car that's going to drive itself. So generally, you have an agent. It needs to be able to observe the environment, take an action to modify its state in that environment. So it's reading the state, taking actions, and then from that action, see what the reward is. Does the change in state help me? Unsupervised learning, changing gears. Generally, when you do not or cannot have labels, so you're going, what's labels? Hold on to it for a second. It'll all become clear. It's generally comparative in nature. So you can have things like feature extractors over here, structure discovery, big data visualization, meaningful compression, feature elicitation. So feature extraction, I think, is it's a commonly used one. So I have an example here. You have an original image and you would like to compress it down with AI. You assume some kind of loss. It's extracting the features that can be decoded, if you will, into these images. You can also use it for jumpstarting labeling. If you aren't sure how to label, maybe you can perform clustering to see, there seem to be 4 main states. So we should have 4 classification bins. We'll label them 1 through 4 because we're clever and unique. The reason people think big tech is actively spying on you is people are really easy to predict if you think about them in multidimensional spaces in terms of features. So Netflix did some pioneering work, and basically the whole what should I recommend you to watch comes because there's somebody else who has almost identically the same viewing habits you do, and they happen to watch it and they said, yay. So I put you in this cluster, and then I start suggesting things to you. This is kind of what happens when you see the stories in the news about people realizing they have certain medical conditions before family members or before people who shouldn't, because you can correlate, oh, you're searching for these symptoms online. And people who do that and then shop at this place, they tend to whatever. So it can get kind of dicey quickly in terms of that. How it works, I like to think of line of best fit. This is more like creating borders. So I have just an example here of over time, you have some delay, whatever this happens to be. You have two axes, and you've told it, I need you to find me two clusters. So essentially what it's doing is it starts having no idea, and then it starts realizing, hey, I can use these features to determine cluster centers such that I'm minimizing essentially the average distance between any point and its cluster. Kind of a loosey-goosey way, but to understand it. And you can see how they kind of hone in on these two clusters, and then you spend the rest of your time and life quibbling about which cluster those should belong to. That's your job. So you need to choose those clusters, though. You need to say two clusters. If I told it three clusters, you might get one here, you might get one here, you might get one here. And the general rule of thumb, as you choose more clusters, you get closer and closer to having a cluster size of 1. So if you came in and said, I have 100 points, I have 100 clusters, what you're going to get, if everything is working right, each cluster, each point is its own cluster, which is probably less useful than you would like. So there's some ambiguity then on whether 2 clusters or 3 clusters is better. And when you can measure things like revenue, you can make some determinations about which features correspond to which of the K clusters. Supervised learning. Now we get into labels. So these are expert-driven systems. And the reason I put this last, even though I mentioned labels before, is because this is what I did for Hydra. So you have to have labels. What are labels? You have to know when you're right. You have to have a target value. These labels can be expensive to obtain. So if you're talking about medical imaging, you have to have a radiologist, or you have to have an oncologist who looks at the scan and says, cancer here, not here. And their time can be very expensive. For deep learning, you may need hundreds of thousands of examples. So you got to find people who can accurately label hundreds of thousands of examples to do a good job. Fun fact, you've actually been training AI for years. Anybody remember the old CAPTCHAs with like the letters, and you have to find the letters? You can still find them around. I'm not saying they're gone. And then like one day, it just like switched, right? Let's make sure it's there. It switched to cars. Where's the crosswalk? Where's the stoplight? What's the stop sign? Help me. The reason why is in the early days, we were doing MNIST. We were doing like letter recognition for mail sorting and those kind of things. So you just get crowdsourced to do that. Then we started doing self-driving stuff and image processing. So we switched. Now you guys are helping train computer vision models, which are already really good. So I wonder what's coming next. These tend to be, you take a picture, you have a graduate student or graduate student or whoever to color in and block off. This is the background, this is the foreground, this is the crosswalk. And you're trying to say, I want you to paint these colors, and I want you to paint these colors accurately. So 2 main branches, classification, regression. It requires a loss function. Unironically, most of the time when you do, oh, do you have a question?
Yeah.
Yeah, go for it.
Deep learning just learning or classification with lots of labels?
Lots of layers. So we'll hold on to that thought. We'll be there in like 2 slides. But the general thing is deep learning is very, very big networks, which often requires lots more examples. I don't know why it's. Oh. Doesn't have a clip. Okay. I think it's That's a little loose. Okay, thank you. So this loss function is the main driver of you doing the thing. The training stuff actually is kind of easy, but sometimes finding this loss function, really, really hard. What is a loss function? How far off are you? So if you're doing regression, it could be mean squared error. I want you to get the smallest error, mean absolute error. Maybe you want whatever custom function you have for saying the output of the model is X, the label is Y. How far apart is that? And then you're just altering the trainable parameters to minimize the loss. You do have to worry about all the typical fitting issues. So local minima, errors, concave versus convex error surfaces, these kind of things. So you have your labels, you have labeled data. So each one of these would have the label lion. You do some training to minimize that loss. You can then predict on test data and hopefully correctly label them, correctly predict the labels of your test data. So a lot of times pop culture, they say machine learning, people go neural nets. It's not really correct. Neural nets are a subset of the broader thing of machine learning. But they're the cool part in my opinion. They're fun to play around with. So I'm going to give you the brief anatomy of a neuron. Neuron takes in input. For each input, it weights the connection to that input. You can think about it. How important is this feature or value to me, the neuron? Then what you do is you add in some bias, it's just baseline, and you add it all up. You're not done though. We need to activate. We need probably some nonlinear component, or else we only do linear sums. That's boring. That's not exciting. Okay, I can be fine. But you pass it through an activation function. So you take your output, you run it through some function to produce an output. This output you can think about as possibly being the input value to another node. You can start stacking them up.
So there's lots of activation functions that you could choose. How do you choose the right one?
That's a great question. I hope I'm not gonna get in too much trouble. You get a sense, like if, for example, I know my output cannot be negative, then I do not want an activation function at the end, which allows for negative numbers. So like ReLU or whatnot. Oftentimes it's part of your hyperparameter optimization. You need to try and see which ones work. And different ones can be better or worse, depending on which features are being extracted from the data. So I wish somebody could get up in front and say, here's the recipe for doing machine learning, go forth, easy peasy. No. Do you have anything to add?
If you wait for about 40 minutes, I will show.
And you can do custom activation functions too. So you can go way off the deep end on doing exactly what you want the node to do in a hopefully nonlinear way. Sometimes it's linear. I mean, you can't get away from it, but good. So you have these neurons, and now we're going to hook them up. So to get to your deep learning question, instead of having like one hidden layer, you may have 50, 80, 100, 1,000, tens of thousands of layers, depending on what you're trying to do. I can't remember what GPT-3 has, but they have models now that have like 1 trillion parameters. Yeah, crazy stuff. So here's math. I'm sorry, here's math, okay? It's after lunch. You take those weights, you multiply by the input, you add in the bias, you sum them up, and you pass it through that function. That's why I did this, because it's kind of read left to right. This is in a feed-forward configuration. So if you want to dive even harder, it doesn't have to be feed-forward. A lot of time, pop culture, when somebody says neural nets, they're speaking of feed-forward often. But you can have things called skip connections, where maybe this isn't connected to this one. It skips over and connects to a different one. Maybe you have LSTM nodes, which again, you can go Google these acronyms. I don't really want to get into it because those nodes will take its output as input for the next time you go through. So this is only one topology, but I think it's the easiest to grasp, and you can kind of extrapolate out that understanding across the various methods. So you start here with input. They go through a node. Typically, the input layer, weight of 1, bias of 0, like it's just the input. You just want the input raw. These could be engineered features. Maybe instead of the values, you're passing in the mean of some set of values. How do you know what the engineered features are? Oh, it depends on the problem. You gotta try it. You gotta see what sticks, which I'll talk about later. Actually, in my second lecture, I'll talk about a bit about that. And so you're trying to train up these weights and biases such that your eventual output is going to have the same, is going to have the smallest error according to your loss. What if my loss function is wrong? It may not learn anything. So it's very, it can be very touchy at times. In order to train them, you have to do something called back propagation. Oh God, there's more math. Look, gradient. It's essentially the simplest method is called a stochastic gradient descent. Do some Googling. You start noticing how do you multiply, or how do you alter the node weights and biases? Well, you can do that by looking at the difference between what you want the output to be and what the output is. A difference each time, each epoch is called, once to the data. So that's like that's a derivative. So depending on that feature, that's a dimension. So you're basically taking the derivative partially across each of the different dimensions, which are the nodes. And then you can take that and figure out how you're going to modify the weights and biases. And you're going to do that all the way up. This is actually the part that caused a lot of problems in the olden days with neural nets. There's something called the vanishing gradient problem. You can't make them too deep. And then there are tricks that we've developed and resources and we have now at our disposal that actually gets around that. So modify the weights and biases based on the loss value, backwards, layer by layer, node by node, all the way up. And you just repeat, repeat, repeat until the loss, the mean squared error, say, is reduced and you're at a minimum. Is it the right minimum? You have to test it out, you have to see. Stochastic comes in because it is often not feasible to do individually example by example. So you form what's called batches, and then you do stochastically the same thing. But again, a lot of math. Just think about it. If you're taking a gradient based off of the answer that the thing is giving you and what you want, I'm working backwards, propagating that backwards until you have new weights, and then you run feed forward and you do those differences, and you go back again, feed forward, back propagate. There's a special kind of node near and dear to my heart, which I'm going to use when I talk about Hydra in just a moment. Oh God, more math, it's everywhere. So essentially in convolutional neural nets, you typically do it on inputs. Doesn't have to be image inputs. Some matrix, there's conv1D, which is one-dimensional data. There's conv2D. Can you do conv3D? Sure. 5D? Yeah, yes. Depends on your problem. But at the end of the day, you have these things called kernels. And so what I'm showing in this animation, or what is being shown in this animation, is the kernel being moved or strode with a stride of 1, being moved across the image one by one. And you're multiplying, you're doing the matrix multiplication. And then you're getting the features out of the matrix multiplication. Usually there comes with like a max pooling or you do min pooling. And so based on the set, you can reduce your feature size, your image size, if you imagine that. So this is just an example. More interesting is different kernels produce different output or features. I'm calling them features now. Different kernels extract different features. So you have a starting image and you can see here the kernel is going to be changing. And kind of the highlighted features on this building. So that one might be good for identifying roofs. tends to highlight things that are above, features that are above. One for Windows, one for X's. I don't know. It depends on what you're doing. So you're really training a convolutional layer to extract the optimum features from its input to minimize the error on your loss function. Okay, I'll say that one more time. You're trying to come up with the optimum kernels such that it takes hopefully the right features, whatever those happen to be, to minimize your loss function in a feed-forward neural network. Okay, so it's a lot of stuff. How much of that do I need to know for the rest of this? None of it, maybe. I mean, it might help some. Okay, but I'll make it very clear. When I started this project, I like to call myself a well-read novice. I dipped my toes into some papers. I didn't have much time, so I couldn't like build my own neural networks and do my own backpropagation. But there are people at Google, really smart people at Google, and they just did it for me. So we're all good. So what we have with data quality monitoring essentially is modern detector systems. They're highly complex and they're interconnected. Highly complex and interconnected. AI is good at multidimensional correlations. Multidimensional correlations, yes. So they usually have a narrow operational envelope. Maybe you have multiple ways you're running the experiment, but in each one, physics dictates how you're configuring things. You want to extract a certain kinematic region, so you move your detectors to meet that. And you typically don't have a very broad, like, that detector can sit anywhere, we're good. You tend to have a lot more confined region. You need multiple levels of checks and controls. There are plenty of unknown unknowns. Okay, what if the electronics goes down? Okay, no, I know that might be a possibility. What happens if a storm comes? A storm? You'll see in my second lecture, that can be problematic depending on the size of the storm, with things like drift chambers, depending on how much background you've had. So we need multiple levels. We need to be able to say, you're working correctly, or we need to tweak the voltages to bring it back in line. We need to calibrate things. So we have to have multiple levels of checks and controls. And it's not necessarily only for uncorrectable issues. Typically, this will be focused on the go, no-go, because we're in the counting house taking data. That tends to be the predominant thing. Is it's 2 a.m. and you go, do I call the detector expert? Do I need to do that? Is it serious enough for that? So how Hall D does it is this kind of flow chart. We have a program called Root Spy, which operates at the minutes level. So every minute it'll update the plots. And hopefully shift takers are totally watching this all the time. Totally. And then there's even like a reset button, which will blank out the histogram so we can see if something developed. Because you don't want the current statistics to overwhelm new holes. We'll just look at inefficiency. And they totally always hit that button when they're supposed to, and always diligently watch it and totally keep careful, detailed notes in the logbook entry. God, I wish this was true. I'm lying to you. So on the hours level, we produce something called incoming data. So there's more plots that are getting produced. These are like fundamental occupancy forms. Are the stuff on? Does it look on? Are we getting data in? This is good, yay. But incoming data can be a little bit more calibration based, a more detailed look. Maybe it's not feasible to do on the fly online. We produce them in the coming hours after data is taken. And hopefully the detector experts are looking at this data and talking with the shift takers because they get perfect notes. And so those people say, something seems to be going off. We're losing, our timing resolution is bad suddenly. Maybe we need to tweak something. We need to get a replacement part. And so they totally always, though, they always catch everything. So every day, this line was me. I was the online monitoring coordinator. I would look over the previous day's running. And I would try to see if they missed anything. And of course, I never saw any. Like a lot of times, I saw stuff. because 2 a.m. weird stuff happens at 2 a.m. And then I talked to the offline monitoring coordinator who would do what's called monitoring launches. And in the coming weeks, we look, can we reconstruct the data? How well? Let's test. Oh, we maybe need to tweak calibration constants. Let's test. Oh, okay, now let's actually redo the reconstruction. Now let's do an analysis launch. Do we reconstruct the particles we're expecting and the rates? What's our resolutions looking like? Oh, there's something wrong. Let's do another monitoring launch. So this is a cyclic thing. And that's done with the aid of the analysis coordinator who's talking to all the collaborators and saying, our kaon separation isn't looking as good or whatever you have. So this was me. I lived here. And so I wanted to play a quick game because after lunch is recess. So let's play a game. And I realized that this Dragnet reference is probably going to go over a lot of people's heads because I think I'm even on the younger side of somebody who gets a Dragnet reference. But we're going to soldier on. So the story you're about to hear is true. I have changed the names to protect the innocent. I'm not going to show you my logbook searches. A lot of times they're not interesting. No, nobody said anything. What's going on now? That's great. So question to keep in mind, what is the problem? Is it isolated? Is this due to running conditions or maybe some test? Should we stop taking data and call the shift crew? Do we call MCC? Do we call the detector expert? So it is 5:15 in the morning. Yes, you read that right. This is motivation for me getting a computer to do this because 5:15 in the morning. The email has just come in. I'm not going to show you all the plots from all the runs at GlueX. Basically, I'm going to be focused on occupancy plots, which give me the rates of detector sensors firing, the beam properties, the physics signals, and trigger status. I'm not showing you the logbook entries and not showing you about 20 other plots that I checked. So, an abridged 5:15 in the morning. Oh, these plots. Oh God, what is that? The occupancy changed in the BCal. What is the BCal? It's our barrel calorimeter. It doesn't really matter. Anomaly detected. So somewhere between this run and this run. Well, if you squint, it might be right there. It's fainter. So maybe somewhere around here on this bottom row, we need to look for a change. A beam looks fine. This is our amorphous. These are diamond, as they should be. This looks reasonable. This is fine. Oh, the CDC gets dimmer, our central drift chamber. It sits inside the BCal. You can see it's bright yellow here, and that kind of dims. But remember the two numbers. It was here versus maybe here-ish, or certainly between these two in the BCal. So this dimming is probably uncorrelated. Maybe beam intensity changed or something. FCal, our forward calorimeter, that looks fine. Oh, there are a few more dead modules. I should probably tell Colin, but Colin isn't here right now. Got a new person. We had some base problems. We need to go in and change them. I looked at 13 more plots. Oh, physics signal. Oh, look, row. Row looks fine. And then they're phi and pi zeros. They look fine. They're all there. They're a little scuzzier. This is online, rudimentary calibration. 5 more plots. Oh, you probably can't see that. There's a green bar right at like 1. The fact that you can't see it is a good thing. You see how it's right there now? Interesting. Increased dead time here. So likely several BCal modules have become noisy, contributing to increased dead time. So this gets noisier. BCal is part of our trigger, which I know because I'm at GlueX. You didn't know that. I knew that. But it likely happened. I don't know why. It's 5:15 in the morning. I don't know why. Probably by now it's like 7 in the morning, and I don't know why. But it probably happened during run 42351. It's not impacting our physics data. We should probably tell the detector experts not at 5 in the morning. Morning meeting, 8 a.m. is fine. I'll let them know at 8. And we should probably investigate further. We might need to go into the hall. In less than 24 hours from seeing this, from putting in my brief, from discussing it and going into the hall, noisy components in the BCal were found, replaced, they kept running. There are definitely plenty of issues, not alarmable in the traditional sense. So a lot of times, high voltage alarms. If you take in a shift, if you take shifts here at the lab, a module electronics will go down, and there's an alarm system that says, "Hey, I think this is supposed to be on," and it's not. And that's easy to detect. Here's a plot of our FCal running, and here's like another plot. And I noticed there's this halo. So I wrote my brief, weird halo in FCal. And it turned out that again, less than 24 hours, somebody left the red light on in the FCal. And the red lights are up top, which increased rates at the periphery. No alarm was detected. The shift crew should have caught it, but they didn't. Shocker. They got a lot to do. So every run produces an initial 22 plots. This is an underestimate now because people only add plots, never remove it. More thorough monitoring is performed offline, produces 109 plots. With 2 to 3 hour runs, 175 to 875 plots to look at. I didn't do that. I'm not that much of a masochist. So I looked at closer to 175 plots. I wanted a machine to do this. There's no reason a machine that can't aid in looking at them. And keep in mind, sometimes a single plot, like our little game, it's not an indication of problems. Maybe you need to look at multiple to really figure out what's going on. I'm doing a trigger study. You didn't put it in the logbook and everything looks messed up. Yes, because it was a trigger study. But you can only really tell that because you look at several plots and all of them look off. So trigger studies is a big one. They all look like big problems. I got called in by the hall leader. Did you look at the plots this morning? I'm like, oh God, yes. What did I do? Went to his office and he goes, did you see this? I'm like, yes, it was trigger studies. Are you sure? Yes, it was trigger studies. Nobody wrote it in the logbook. I had to ask around. Bane of my existence, that logbook. So being at 5:15, I know there have been advances in hardware and there are frameworks. So rapid advancements in machine learning. And AI can detect cars and people and read signs in real time. It should be possible to build something to look at these images for me instead of me. And
sorry, that was just you use 35 minutes.
okay, great, perfect, thank you. So what is involved is a lot of pattern recognition and paying attention to the correlations between plots, coupled with domain knowledge. And I put bold on the pattern recognition. I think this little box is gonna drive me nuts, ultimately. So, so the pattern recognition, that's because I knew it's in the trigger. I knew how these things play together. And then the correlations, so multidimensional correlations, ML. Domain knowledge. So this is the only part. Can we teach this? Maybe we get the experts to teach it. So when a plot A looks like X, plot B should look like Y, but it looks like Z instead. And by looking at plot C, we can probably gauge that, guess that Q is wrong. Yes, alphabet soup. But the point is, this is the kind of thought process that you go through where you fill in the placeholders for actual plots. This is exactly where AI can shine. It's in high dimension and highly correlated multi-dimensional stuff. So large multi-dimensional data sets full of correlations. There was the Amazon representative, Amazon and AI, and he listened to a talk on Hydra. And he said, no offense, no human should be doing that. And I said, oh no, I don't take offense to that. I don't think a human should do it either. I've been doing it for 2 years. So yeah. So there are many considerations in developing and deploying AI models. Data collection, so how are you going to get your training data? How are you going to test the model? How do you know when you're done? Labeling, this is supervised learning, so labeling. How are you going to label all of your data? What will that cost? Generally, admin will get kind of upset if you go take all the detector experts and say, stop what you're doing. I need you to label 50,000 of these images, please. The model development, how are you going, what are the requirements? Are there fixed interference times or error rates that are unacceptable? How will it work? And then there's the sociological implication. How are people going to interact with the system? Are there any barriers to deployment from the human side? If it's more annoying than the system that's already in there, and it requires more work by the shift crew, they're not going to do it. I wouldn't do it. So this is a picture of me when I started on Hydra. And so I asked the question, can we leverage computer vision? I was interested in computer vision. I had no experience with AI and ML. Okay, I did if-thens. I was good at that. So I had no experience with ML. I'm interested in computer vision. And I perform it by looking at images. Maybe I can get it to do it by looking at images too. Are there off-the-shelf technologies I can employ? This is going to be a side project. I'm not really supposed to take cycles on it. I don't have dedicated resources there. It's not funded. This is like a weekend thing because I'm trying to not have to wake up at 5:15 in the morning. And I have no experience doing this. So the more I can kind of part out, the better. Well, data collection, I already had the raw data. Logs already had all these monitoring plots from all the detectors, from all the runs in image format. I actually worked on the web page that collated them before starting this project. So I already knew where they were and how they were arranged. This is slightly wasteful in terms of what data you need for inference. You have many pixels that represent the same value. I get it. I did it this way because I knew where all the data was. And I thought it would be the easiest way in. I get to use all the developments of machine vision, convolutional neural nets in particular. I have my own. This cuts down on startup time. If you come away with not much else, I'm an exceedingly lazy person and I will work so hard so I don't have to work again. That's my philosophical view on the world. So labeling. I made this labeler, quite proud of it. I'm not a web developer. So I made this web page. This web app allows people to paint labels on the images very quickly. It's accessible online. You can log in and label hundreds of images in a minute. They tend to be very easy to do. Yeah, so it's very, very fast to label it. I won this plot type. Took me 32,000 images. Still worth it. And you get a good sense of like, this is good, this is good, this is good, this is good. And you can see some broken stuff. That's probably bad. No, it's pretty quick. It's pretty quick. Okay, now I need to worry about model development. Introducing the Inception v3 network. It's already in Keras and TensorFlow, which I was going to use. Done, model development done, as far as I'm concerned. I needed something that I could get off the ground, prove it works. Once it's working, I can go refine. This is the topology. This is a deep network. You can see by all the modules. These modules are really multiple layers. And what I would say for Inception v3, like all the other Inception networks, is that instead of having one kernel size, which has a certain feature resolution, if you will, have a bunch of them, and then put in mechanisms so they can vote. I see this tiny feature. I think it's very important. I see this big feature. I don't think it's important. And so they kind of all vote, if you will. so that you can classify at the end. This is bringing an atom bomb to a knife fight. If I were to approach the problem novelly now, there are much simpler networks which you can use, I have used, to get the job done. But this is what's in there. And I really wanted to just underscore the fact that a lot of the stuff is off the shelf. So if you're sitting there going, I think this is a good problem for AI, but I don't know. You don't necessarily need to try it out. So inspiration, Miss Frizzle, try something, get messy, make mistakes. So there were some challenges though in training. I have unbalanced data sets. So 80% are good, 10% are bad, 10% might be other. This can lead to biased inferences. So you can think about, the machine goes, I don't know, average, because that's the smallest error it can get. It doesn't know what to do with it, so it just kind of returns to the mean. You have lack of examples, so especially the problematic states. This board has only gone out twice in the entire history. No other board has. It'd be really nice if all the other boards have, but they haven't. So the machine doesn't necessarily have examples for all these problem states. That could be a problem. Again, unknown unknowns. So there are ways to deal with unbalanced labels, small data sets. One thing you can do is super sample. Here's a good one. Look, this is a problem one. Same problem again. See, it's problem one. Yep, same. It's definitely a problem. And what you're trying to do is artificially bump up the labels so that you get a balanced label set. There are problems with this. You're showing the same image. So it's like teaching my son the difference between a cat and a dog, but I only show one image of a cat and there exists dogs. He's probably not going to do a very good job of generalizing that cat. Smart kid, but I only show him one cat. It's hard. There's something called K-fold. You can quarantine a test set and repeatedly train a model. So you go by fold, you block off one for validation. Validation isn't used in back propagation. It's telling you how good the training tends to go. It has access to the labels for it, but it's using it just to test kind of the generalization. If your validation set is disjoint from your training set, you'd be hosed. Unless you do K-fold, in which you take that validation fold and you move it along your blocks of training data. So that way, at the end, you have a model which has seen all the data in times, in -1 times, and each block it's used as validation exactly once. These methods increase training time, sometimes a lot. Instead of doing one training that might last a couple hours, you're going to do 5 of them. Now it lasts 10 hours, which may be worth it, depending on your problem. I came up with something called strategic undersampling. There might be a technical name. I don't know it. So because we have that narrow operational envelope, when you've seen one good plot, you've kind of seen them all. You've seen one empty histogram, you've kind of seen them all. There are many, many ways it could be wrong, but a smaller subset of ways it will be right. So we can exploit this variance, or relative variance, to undersample the lower various labels. So instead of showing it 100,000 empty histograms, we show it much less. We randomly choose from it such that we equal those bad labels. In this case, remember I said 10% bad? That's really what we want, is to do a good job on the bad ones. So let's undersample the good plots and show it far less data. This increased training speed by about 5 times with no loss in model accuracy. I think I can only do this though because the blank histogram I think is a good example. Once you've seen one empty histogram, you've seen all the empty histograms. But that board being out versus this board being out, 2 different histograms. To deal with the lack of examples, we can also use simulated issues. I put simulated. I argued with my now boss on what we call this. It is not from simulation. It's not Monte Carlo. It's from real data, but it's not real data. We modified the real data to make it look like it. So we simulated, but not Monte Carlo. We photoshopped. That sounds bad. So we modified the real data histograms to emulate this board being out, or maybe an inefficiency here. We could use this to test for overfitting. Did it get this one right? That has never happened before. It hasn't happened since. We just pretended it did. And when we first did it, early days, no, it didn't get it. It was very overfit. It knew if this board went out, which has happened, that's bad. This one goes out. I don't care, I guess, because they never told me that was bad. So we generated actually all single board combinations and all two board combinations. I used a small subset of these issues, single board issues, and was able to then accurately generalize to all single and two board outages, even some three board outages. So it is able to generalize from a small subsample, but if you've never shown it to them, I'm gonna personify it. That's my friend now. If you don't show it an example, it's never gonna learn it. So I'm going to introduce Hydra. I have like 10 minutes. Okay, question.
Could you go back to the previous one?
Sure.
Do you have to change that white section around for each board?
Yes.
There's a new one, this section is now broken too.
Yes.
That sucks.
And, well, you make an algorithm to do it. So the computer does it, generates the thing.
It learns Photoshop, it knows.
Exactly. Yeah, pretty much. David Lawrence actually wrote a plugin that basically said, "Oh, you're part of this board. No, don't worry about it. It didn't get hit." So we just ran over data, and you just march through combinations of boards. So it took a half a day to develop, implement, and get data. But yes, in principle, it can be really awful. So you get a computer to do it. So the computer can help teach the computer to do it all. So this is Hydra. This is Hydra. I like having the image. It makes me giggle because as I play Dungeons and Dragons, I am a geek. I like imagining that inside Hall D, 2 a.m. you're on a shift and the Hydra is getting anxious and hungry in the back of the counting house. But really, Hydra aims to be an extensible framework for training and managing AI for near real-time monitoring. The reason I call it Hydra is because what you'll see is each head works on different plots. So you have a CDC occupancy head and a BCal occupancy head, and you have a physics signal head and whatever you want. If you want to tell cat from a dog, I can put that in the database and it'll work. Yeah, other question?
So do you have like 175 things?
No, not yet. We're working on it. But yeah, this is the scale that I have to target. I really want everything to be in here. How do I scale up the system in a way that I don't have to do much? I don't want to do work. So yeah, in the end, yes, I should have hundreds of heads and hopefully a body to put them on. So most importantly, Hydra allows me to embrace my inner sloth. No, not today. I cannot understate this enough. I'm so motivated by not having to do this anymore. I'm going to spend a lot of time and energy to never have to do it again, to prevent my fellow mankind from never having to do it. So where does Hydra sit? We have our accelerator. Here's Hall D, way over here. This is our detector, so we get beam. We produce these histograms. Hydra eats them. And then produces output or classifications for the different plot types. That's where it sits. It sits right here. The shift worker is safely placed on the other side of the computer. There's a backend. So I made a database, and it stores all the plots for labeling, all the user-defined labels, all the models, the locations of them, not the models themselves, all model classifications with confidence for the saved plots. And the training is virtually push button because I'm lazy and I don't want to have to manually train 175 of them. I want to say like, hey, you train plot A now. Walk away. Done. And I can get these. This is an early result as an example. I don't think this is our latest results, but it just as an example. This is called a confusion matrix. Okay, I'm getting there. What Hydra thinks, bad, good, no data. What the experts think, I put truth here. Sometimes people are wrong. Bad, good, no data. Ideally, it would just be populated on the diagonal. It's not, though. Hydra thinks it's good. Expert thinks it's bad. This is bad. This is the worst case scenario. It only happens 65 out of like 30,000 times. So I think you're not too paranoid. And what's being shown is the confidence that Hydra had in making its determination. So you can see when it gets it wrong, like for here, it's not strongly peaking. It's not very confident when it gets it wrong. Over here, it's more confident. Huh. Okay? And that can tell us something. So that's a problem. The detector is on fire, and Hydra goes, yeah, fine. So we need to concentrate on those most importantly. These are annoying. People don't like these. This sounds an alarm, and it's fine. So it's your smoke detector going off, and you're not even cooking. Change the battery. Couple anecdotes real fast. These plots look the same. Both of these look good to me. The expert labeled them both as good. But the left one, the AI said was bad. The AI caught it. And if you squint really hard, I know you can't, especially in the back, read it. The scales are way off. And the distribution is a little more narrow and choppy. It was right. The AI was right. It was able to detect a problem here that the expert didn't when labeling. That's harsh to the expert because they labeled a bunch of these correctly. That's the only way it learned how that is wrong. This is my favorite example. Labeler was told less than 100,000 events, no data. I'll quibble with that philosophically, but no data. On the left is a good plot. On the right looks like a good blob. Nope. The user labeled it good. AI thought it was no data, very confidently, no data. And you look right here, that is less than 100,000. It was able to pick out that rule. I didn't teach it what these numbers are. I didn't teach it numbers. It's probably going, wow, there are these added sludgy black pixels over here that aren't here. And every time it's no data, it's not there, but this looks good. So I'm gonna say no data. So I don't want you to get the wrong impression. It is not, yeah. It's really taking a subset. It saw a problem actually during running. The experts missed it. Everybody missed it except Hydra. Yeah.
So you're just giving it image data, right? Not numerical data?
Just image. Yeah. Limitation, need broad buckets. I don't have a ton of examples. If you're going to classify cat breeds, you need to have lots of examples of each cat breed. I have problems, not lots of examples, a lot of different problems. Deep learning requires a lot of data sometimes. Beyond the scope of this talk, MLOps. Now it's in production. What do you do with it? We can do generic anomaly detection and multimodal data to develop the capabilities. Just a quick flash. I have like 5 more slides. There's something called GradCam, gradient class activation map, where you're basically saying, what about the picture makes you classify it that way? This was given to me by a collaborator. I don't have any thoughts, but she does. And so she was playing around with this, and you can see where in the image it is looking. So this might be able to provide more context, but I think it's bad because of this region. I don't know what to call it, but look in this region. That's the cancer diagnosis. Not just, yeah, you got cancer. Where is it? It's over here. So we can take a layered approach. Generic anomaly detection methods, usually they're comparative, they're unlabeled, find some distance. You don't necessarily have predictive expectation on what the difference is. So you can imagine using generic anomaly detection algorithms to pass anomalies to a diagnosis. So instead of saying, I feel sick, better go see a doctor, you would go, my condition is anomalous. What could be wrong? And then you go see the doctor. So this would be kind of a layered approach, and I'm almost out of time. Technical issues, so I think I will just not reiterate. Currently, I have a bunch of heads, but really I want to be able to look at connections between the plots. So I'm really starting to work on what I call the body of Hydra. What do I do with all the heads? Right now they're disembodied and all chattering at the same time. So you can think about something like this being multimodal. So there may be opportunities for natural language processing work. Maybe it'll write the logs for shift crews who always keep diligent logs. Well, maybe they'll use the logs along with the images to really make sure things are lined up. Oh, the people said they were changing the configuration. Doesn't look like it happened. That might be quite good. And on the human interaction side, I ripped up another web page. I'm not a web developer, I swear. So this is actually giving a real-time dashboard. If we had the time, you can go to it and you can watch it, and we're taking cosmic data, and you can see in real time what the system is doing, currently up and running. So people operate on trust. We tend to trust other people. I can have philosophical arguments about you, what we trust. I claim trust the other people. You trust the expert's opinion. If you tend to trust your parent, so if your parent disagrees with an expert, you'll tend to, as a child, agree with your parent because you put more trust in that person. You tend to avoid discomfort, so you don't want too many alarms. People just turn it off. People are busy and lazy. So you need to lighten the workload, not add to it. And we are operating in an app-driven world. So how people interact with these systems needs to be intuitive and touchscreen based and mobile and all that fun. So rapid advances in AI and ML tools and techniques allows even novices to begin playing around with AI. Leverage that off-the-shelf technology. Hydra has been deployed in Hall D and spotted problems students have missed. I'm currently working on SBS deployments in Hall A and class deployments in Hall B.
Class detector is
Per
class 12.
Oh, okay, fine. In Hall B, I'm working with anyway. So AI is here to stay. We need to start considering how we're going to work alongside our robotic overlords. I'll leave you with this quote, and I think I'm out of time.
Thanks, Thomas Britton. Does anyone have any questions?
Yeah.
Can you give more details about what's happening in Hall B?
Hall B?
Yeah.
I hear word that there was a detector that had some issue that wasn't properly diagnosed, and Hall D, we were having success with it, so I got approached by actually Nathan Belzel, and he was like, "Hey, maybe we get," and I was like, "Yeah, sure." So actually, right now, while I'm talking, the first model is being trained for class, or for Hall B.
Which detector?
I think the CTOF is the one being trained right now, but we have a few detectors we're starting with. We're doing the inductive approach. Make it work for one detector, second detector, all the detectors. Any other question? Yeah.
I've taken data in Hall D, and so there's a lot of variability that happens when you are the person that's supposed to write down the stuff in the logbook. Are you just, so like we used carbon targets, and so that plot is going to look very different than previous targets. Are you going to try and incorporate that in some way?
We will. There is stuff I didn't have time to quite talk about. I could have probably rambled for 3 hours on Hydra, but it's my baby. There is mechanisms, autonomous network mechanisms for gathering plots, for kind of spotting disagreements or bifurcations in the classification. It's not doing well now. Push button training. Yes, we are. Mechanisms are there. It will be retrained as needed to cover this. Yeah.
Will that not cause a problem in the future? Or are you able to say like, now we're using carbon? This is what it should look like.
Hopefully in the future, it will be able to tell the difference.
Oh, cool.
Otherwise, what you call good, a smattering of different things,
Yeah.
it's got enough capacity to learn those, so I'm not concerned.
More questions? Any questions from
No, not that I see so far.
So I guess we go now for a break of 15 minutes, and due to the situation shift, now we're having the coffee break outside.